Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 4, Lecture 5, Dynamic Atomic Force Microscopy Methods. We talked in the last lecture about prior experimental results that really showed the evolution of frequency-modulated AFM as a key tool for achieving atomic resolution on surfaces. And we really showed that the results that have come out of high-resolution imaging in FM-AFM have been pretty spectacular. They range from the early work that first showed the reconstruction of silicon 111 surfaces to pointed effects, and to these days to the ability to see atomic resolution, true atomic resolution, even in liquid environments. What we will talk about today are the key milestones that have been achieved in force spectroscopy using FM-AFM. I remember force spectroscopy is the process of trying to convert information on frequency shift and dissipation or excitation as a function of Z, to convert that information into F versus D, which tells us a lot about the local chemical structure of the atoms that one is intending to study. So very soon after the images that we talked about in the last class started coming up, the key question came up whether or not the AFM could actually be used, FM-AFM could actually be used to come up with a quantitative estimate of the tip sample interaction forces involved, especially in the case of surfaces which are reactive, for example, silicon 111. Remember, I talked about the fact that contact mode AFM imaging for at atomic resolution typically did not use reactive surfaces because the interaction forces would become rather large. So the whole idea would be, can FM-AFM be actually used to quantify the interaction forces between a silicon tip and a silicon 111 surface came up. And one of the earliest works that actually demonstrated this was this one out of Lance and co-workers out of Ernst Mayer's group in Switzerland. And what one sees in the top left here are atomic resolution images of the 111 silicon 111 surface. And what one notices in this image is that if you look at where the number 1 is written, there's actually a hole. There's a defect in the sense that there's a silicon atom that's missing. And then there are two other add atoms next to it, number 2 and 3. So 2 would be a silicon atom which has a neighbor missing, and then 3 would be a normal atom on a surface which has 6 neighbors on the same plane. Now these experiments were done at ultra high vacuum conditions, extremely low temperature conditions, and with the high stability that was achieved, it became possible to actually locate the tip above 0.1, above 0.2, and above 0.3 and approach the sample and measure frequency shift as a function of Z. As you can imagine, this is an extremely difficult task requiring extremely stable atomic force microscopes that can actually do this without drift between the tip and the sample. So what one sees in the top right were pretty remarkable results that suggested that the force FM-AFM was able to detect the differences in interaction forces between the atom on the tip of the AFM cantilever and these 3 sites. Site 1 is a hole, site 2 is a silicon atom that has a missing neighbor, and then site 3 is a hole or normal silicon atom on the surface. Remarkably, if you look, for example, there's definitely a different signature of the frequency shift versus Z on the hole or on the defect. And one can also tell in the inset on the top right, that the frequency shift versus Z is different, has a different signature for 0.2 and 0.3. So this was a very exciting result when it first came out. And what was done with this study further was some quantitative estimates were made about the forces involved, using the kind of inversion reconstruction formulas that we've already talked about. And what you see on the figure in the middle on the right is the reconstructed force, the conservative force on the hole, or on the vacancy, if you will. And what one notices is that the interaction force as you approach the sample has this attractive feature as it goes down. And what they did was they had a model for van der Waals interactions between the tip and the sample, and superposed over the experimental curve is a fit of the van der Waals model, and the fit was excellent, suggesting that van der Waals forces dominate the tip sample interactions when the AFM tip is approaching the hole, which was expected according to the conditions that were investigated in this study. On the bottom on the right is shown the reconstructed force in red over the site label 2 on the sample. And one notices a gentle attractive force and the sudden sharp decrease in attractive force, and actually the force starts turning up around. This is very interesting, and what they did here was then to sort of propose that when you look at the force reconstructions, there are longer range forces such as van der Waals forces, and when I mean longer range, I mean that are active at distances of up to 10 angstroms. But the chemical forces, which is what was the goal of this research, was to see if one could actually detect the chemical force between silicon atoms, would become active at much shorter distances, typically 1 to 2 angstroms, when the gap is very small. And so what they did was they fitted a van der Waals force law to the longer range forces seen here. They subtracted that out, and what one was left with was the yellow curve. And the yellow curve had a minimum of about negative 2.5 nanonewtons. So based on this, they were able to quantify that the adhesion force required to pull apart a silicon atom on the tip, and the silicon atom being studied was quantified as being about 2.5 nanonewtons, which was an amazing study to be able to come up with that estimate. They also compared this with ab initio calculations, theoretical calculations, and found that the numbers were actually not too far as the magnitude of the force was concerned. There were difference in slopes, force versus distance slopes, and were slightly different, and all these were attributed to relaxation processes and other things that were not necessarily included in the theoretical model. So following this work, there was more of an interest in applying these techniques to surfaces where there were multiple kinds of atoms that were mixed on the surface, not just looking at surfaces with defects, but looking at surfaces where different kinds of atoms would be deployed on the surface. And this brings us to the issue of surface binary alloys. And I just want to do a quick aside on what they are really. But surface binary alloys, has in the recent, let's say, decade, been a very interesting, intense field of research. Why it's interesting is that if one looks at, for example, the properties of silicon, the electronic properties of silicon, there's not much one can do about it. Lattice spacing is fixed, and so the idea that one can put on the surface of silicon other elements that are shown, for example, in the red box on this periodic table, and that these elements, the atoms in these elements, can very easily integrate themselves into a silicon surface, thereby completely changing the properties of the silicon surface, make this a very interesting field, because alloying the surface allows one a degree of tunability of the surface that is very rarely encountered in other situations. So the idea that one can take a silicon surface and then just evaporate atoms from germanium, tin, or lead on it, heat up the surface, and cool it back down, and the atoms that when evaporated sort of completely integrate themselves into the silicon surface, completely changing lattice constants, electronic properties, all within a very thin thickness of the surface. So there's a lot of interest recently in studying surface binary alloys, and very soon after the results that I just showed you before, there was an attempt out of Morita's group again in Japan at applying FM-AFM to study binary alloys, in this case tin silicon alloys. Now, what one sees in this work are topography images taken in FM-AFM in UHV conditions, and what you see going from left to right is actually an increasing amount of coverage of the surface by silicon. So basically in each of these cases, certain amount of a monolayer of silicon is deposited, certain amount of monolayer of silicon is deposited, of tin is deposited on the silicon surface. Surface is heated up, brought down to room temperature, and the tin atoms basically completely reintegrate themselves and become whole with the surface that one is trying to image. The bright spots actually are the tin atoms. They stand up a little more. And you can see as you move to the right, you get increasing coverage and you start getting more and more tin atoms. Now, I want to emphasize that the structure of this surface is interesting in the sense that it's not that the tin atoms are just sitting on top of silicon and the silicons are like defects. It literally is the fact that if you've got a silicon atom and a tin atom, the silicon atom is being acted upon by different forces beneath it compared to the tin atom. In particular, one can demonstrate that a silicon atom sitting on a silicon surface is going to experience higher forces pulling it down, in effect, due to the presence of an unpaired orbital on the top of the silicon. On the other hand, if one has a tin atom sitting on a silicon substrate, it's not pulled down with as much force. As a result, the tin atoms appear higher than the silicon atoms in these images. The other important thing to point out here is that if you look at the image all the way on the right and you actually measure the lattice spacing of the unit cell, which is now formed of the surface tin atoms, the lattice constant has become about 3 times that of the silicon lattice constant. So this really suggests that binary alloying allows a degree of flexibility and tuning to the surface, which is pretty remarkable. The ability to be able to change lattice constants by nearly a factor of 3 is the reason why binary alloys are very important, are a very interesting subject to be studying using FM-AFM. So in this particular work, once you can figure out where the tin atoms are and where the silicon atoms are, the tin atoms are a little higher than silicon atoms, it becomes easy to go ahead and actually do force spectroscopies on those individual atoms. And this was accomplished again by this group, and what one sees in the top left are graphs of the frequency shift versus Z approach distance. One is taken on the tin, which is the one shown in black, and the red one is the curve on silicon atoms. And when the Sater-Jarvis reconstruction formula is applied, and this data are converted into force versus distance, one notices that there is a very distinct difference between the interaction forces between the silicon tip and a tin atom, and a silicon tip and a silicon atom. In particular, I would try to draw your attention to the fact that on the silicon, the interaction force curve is actually deeper. It goes down to a smaller value, more negative value. In fact, the maximum attractive force one gets between the silicon tip and the silicon atom is between between -2 and -3 nanonewtons. And if you recall, this is very similar and not far from the results that were obtained by the previous paper that was discussed between silicon and silicon. The interaction between the silicon tip and the tin, on the other hand, does not reach such high values of attraction. On the other hand, when one approaches the tin atom, one can argue that the slope of the attractive forces is actually a little steeper in the case of the interaction between the silicon tip and the tin atoms. So this became really interesting, the ability to be able to look at atoms and go in and do the spectroscopy on them. The key point being that one could now start distinguishing through the force versus distance curves the interactions between different chemical species on the substrate. So this led to further work in Marita's group and Oscar Kustan's in that group, and what was done is they went around and repeated this experiment on these binary alloys, and they measured many sets of data over silicon atoms, over tin atoms, and they did the reconstruction of forces. Now, what is shown on the top left are graphs of the multiple sets of data that are required, force versus tip sample gap. And, it looks like a big muddle. All the data are kind of jumbled up. But if you look at each set of data, each set we can say is a set is roughly defined as measurements made with roughly the same kind of tip geometry. One notices that for each set of data, consistently the attractive force in silicon maximum attractive force would be lower compared to that of tin. However, when you look between different sets of data taken at different points in the substrate, one would actually find that the actual absolute values get moved around and they really mix up a lot. So the key thought process in this paper was that we see all these data points as you collect different sets of data, and the reason why, or the reason they attributed to the fact that within a set you got a consistent difference between relative difference between the attractive force on silicon and on tin, but that when you went from set to set there were differences, was the fact that when you went from set to set of data, the geometry of the tip had changed. And this has a lot to do with the fact that when you're doing atomic resolution imaging, as we've talked about before, the actual atomic structure of the tip atom on the cantilever tip is extremely important and critical. If one is imaging a certain part of the sample and moves to another part of the sample, and the geometry and the chemical composition of that tip has changed, or the tip has got modified, and the last few atoms have changed in a certain way, then one gets a different tip effectively. And so they realized that one has to account naturally for these changes in tip geometries and the structuring of atoms on the AFM tip. And what they did is they came up with a normalization procedure. So what they did is within each set of data, they took each set of data and scaled the maximum negative force in the silicon to -1, and then they then scaled the rest of the force versus distance graph on both the silicon and the tin accordingly. When they did the scaling for each set of data and then put it all together, all these curves nicely separated into two sets of data, and consistently, relatively speaking, one could tell that the maximum attractive forces on the tin were less than that on the silicon, and that the shapes of these curves really started falling on top of each other. So this allowed a very important result to come out, which is that they were able to claim that the shape of the normalized curves over tin is different from the shape of the normalized curves over the silicon, suggesting that one has now a way to chemically fingerprint each atom that one is looking at, because these interaction forces are mostly due to short-range chemical forces. And so this idea of trying to fingerprint atoms based on their force versus D came out of this, and they demonstrated this to using a spectacular example where they had a ternary mixture, in this case in silicon, tin, and lead. And by doing force spectroscopy on each of those atoms, they were able to fingerprint an atom as being a lead atom or a tin atom or a silicon atom based on the characteristic force versus distance curve. So this was a remarkable result and made it to the cover of Nature. And it still remains a tour de force when it comes to force spectroscopy with atomic resolution. Soon after that, there was an interest in extending force spectroscopy techniques to not only study the forces over single atoms, but over the entire surface. And initial attempts at this would try to do a force versus distance at every point by point of the sample. And if one wants to come up with a truly three-dimensional data set that tells you how the interaction forces change with X, Y, and Z, one can imagine one needs a long time if one is going to do force distance curves at every point. And during that time, thermal drifts could come in, all kinds of drifts would come in, all kinds of corrections would have to be made, and it would be very hard to be able to get, for example, sets where you would have consistent height differences and consistent offsets to all the force versus distance curves and so on. So, key way to overcome this was proposed by Udo Schwartz's group in 2009 when they studied HOPG, freshly cleaved HOPG, ultra-high vacuum conditions, very low temperature, and basically they suggested that instead of trying to do force spectroscopy point by point of the sample, what one could try to do using an extremely stable, very low drift, especially made AFM system, is to acquire images of the sample at different delta Fs, at different frequency shifts, and sort of put all those images together, stack all those images together to do and convert the frequency shift images into interaction forces, which you would then have as a function of X, Y, and Z. The key thing was, the key advantage of this method was by imaging, as opposed to doing, separate force distance curves at every point, one is able to really reduce the effects of Z drift in these images. As far as compensating for XY drift, the figure in the middle kind of shows the strategy for doing that. So after one takes an image of a surface, if there's this XY drift, one can go piece by piece and look for parts that overlap and parts that don't overlap, and crop out those points that have drifted out of the view, in which case one would remain at the end of the day with a part of the original image over which you can actually overlap the data XY in the X, Y, and Z direction. What one sees on the rightmost image here is actually a reconstruction, in this case not of the tip-sample interaction force itself, but rather the potential energy associated with the tip-sample interaction force, which is coded in the color. And then you have X, Y, and Z space. The resolution here is absolutely tremendous. What you see is the X and Y axis are a few hundreds of picometers, and the height is going up to 100 picometers. So it's actually absolutely remarkable that one is able to then study the potential energy associated with tip-sample interactions with high density spatial information in all three directions, X, Y, and Z. So once this data are here, this allows you to actually slice these data sets and study, for instance, force versus distance, or potential energy versus distance, or frequency versus distance at any point on the sample surface. And one can get information on gradients because you have a very dense set of data, so you can get gradient information in all three dimensions, in all three directions simultaneously. So this is a very key development which requires extremely stable AFM systems, and it's causing a lot of interest, and there are many groups trying to pursue this line of research these days. In particular, most recently, there's been attempts at making these kind of three-dimensional force maps on liquid-solid interfaces, and this is recent work that came out of Yamada's group in Japan. This is in particular HOPG in water. On the left are FM-based, FM-AFM-based topography images. On the right is a two-dimensional map along the X direction on a sample. The Z direction plots the frequency shift. So you get a pretty dense set of data using this method. And what's remarkable here is that one sees a very high positive frequency shift as one approaches the interface, and that positive frequency shift is attributed to the presence of solvation shells or hydration layers of water molecules as they assemble or at the water HOPG interface. So clearly this notion of three-dimensional force reconstruction on surfaces with atomic resolution is a key area of research, and we certainly hope to see a lot of developments in this field in the near future. Right? Thank you.